Hey everyone, welcome back. We are, believe it or not, over the halfway point here and well on our way into our advanced topics for multi-level modeling this semester. So now we're going to get into Module 8, Part 2, which I've lovingly called More Fun with Growth Models. Last week was some intro fun with growth models. In this week, we're going to get into just a couple useful advanced topics that I think are nice extensions to the basic growth modeling framework. So let me turn on my presenter mode here, and we can proceed. So we're going to talk about two topics, and I'm guessing this is going to get split into two videos, two lecture videos. The first thing we're going to talk about are what are called linear growth models, or growth models where we add sort of nonlinear effects, which are very useful, particularly when you have measurements over a longer period of time or a larger number of observations. So if you have more than 3 or 4 data points, you generally can start to think about maybe testing for nonlinear effects, which can be very useful. So let's dive into that a little bit. So last week we talked about running and interpreting the basic 2-level linear growth model. And I say basic, although it's not entirely a basic thing. It actually is kind of fancy. So we learned how to incorporate random effects and random slopes to our models. So each person has their own unique starting point and their own unique growth rate. And I don't know if I gave this example in last week's videos, but there's this idea, if you've ever known or had family who tracked a child's height in the kitchen. Sometimes you keep track of how tall somebody is by standing up against the door, and you put a little line over their head, and then you do the same thing 6 months later, you mark it. And so sometimes when you go to a new house or a place where you haven't been before, you can actually see those marks on the wall, and that's actually growth, right? And you can actually track sort of the starting point, so the first measurement of the child's height, and then how they got taller over time, and that's kind of the slope or the change over time. There was an example I used about how you could measure that in Kleenex boxes or something like that. So this week we're going to go a step further, and we're going to talk about situations where we actually have nonlinear change over time. And this is a very useful thing to be able to do, sort of another tool for your skill set. So let's talk very briefly about why measuring nonlinear growth is useful. First of all, linear growth is great. You are able to account for lots of different situations where you're looking at change over time with linear growth. But sometimes measuring growth in a strictly linear way can be a bit simplistic. So one example of this, of course, is thinking about the idea of kids getting older, right? If you think about a child that you might know and their growth pattern, a linear growth model would suppose that a child gets the same increment taller each year, like maybe a Kleenex box taller each year. And that may not actually be very realistic, right? So sometimes, this idea of a growth spurt, right? So kids grow a lot right at once sometimes, and then the growth tapers off for a little while, and then they might hit another growth spurt. And even kids have growth spurts at different times. So somebody might start a little bit more slowly and then get taller over time. And lots of other different ways that you can think about sort of nonlinear change. So in a linear model, we sort of assume that constant rate of growth. And for the most part, that works pretty well. But there are some situations where we may not expect linear growth, and so we need to have a little bit more flexibility. I love the story of the tortoise and the hare. If you're familiar with that fable, that's another really good analogy for this. Believe it or not, back in the day, I was a reading coach for a while, and this is one of the books that we would read when we were using what are called leveled books to try to figure out a child's sort of initial group reading level in school. And there was a good version of The Tortoise and the Hare, so I have some fond memories of that one. But if you think about it, The Tortoise and the Hare is actually a pretty good analogy for linear versus nonlinear growth. So think about the tortoise, right? The tortoise's motto was slow and steady wins the race. And he basically kept an even pace all throughout the race. So remember, the tortoise and the hare are racing, and the tortoise goes at this steady pace. The hare goes out really, really fast, and then falls asleep, right? So the tortoise actually catches up and ends up winning, and the hare, realizes that he's going to lose and sprints at the end to try to catch him, and so on and so forth. So if you think about the tortoise and the hare, the tortoise is actually linear growth. So if we were fitting a linear growth model, that's kind of like a tortoise model. And if it's easier for you to think of it as a tortoise model, do it. Go for it. Because that is a fixed pace over a certain amount of time. So the pace varies very little across time. Then, so a graph for that might look like this. So distance over time. Let me see if I can get my little pointer going here. So here is distance and here is time, and we have this sort of linear relationship between distance and time. So this fixed, so here's our starting point, this is our intercept, and then as time progresses, we move at a fixed rate across a certain distance. All right, so that's the tortoise. Now we have the hare. So I don't know what the hare's motto was, but I just said start fast and then take a nap. So the hare went out really, really fast and then took a nap. And that's kind of a fade out pattern, right? So starting really fast and fading over time. This is actually nonlinear growth. In this case, it's probably some form of a linear plus quadratic, and we'll talk about what that means. Those are some mathematic terms for functions, different kinds of functions. But we'll talk about what that means in just a minute. And so the visual of that kind of looks like this. So the hare here starts really, really fast. So it's almost like an exponential curve, and then starts to fade out over time. And so that is nonlinear. So that's nonlinear growth. It's not the only kind of nonlinear growth that you can have, but it's a common one. So there are actually a number of these types of functions that are used to describe growth. There's, of course, linear growth, which we learned all about last week. So that's a fixed growth rate over time. And the functional form is just sort of the general equation of what this looks like. Not the multi-level equation, but the general equation is you have your outcome here is a function of some intercept, beta 0, plus some growth parameter, which is a function of time. So for each unit of time, you progress a certain amount in terms of according to what the slope is. So that's linear growth. Then we have what's called quadratic growth. And so that is a variable growth rate. So in this case, the growth rate actually increases exponentially over time. So you actually get exponentially faster over time, which is pretty wild. And the functional form for quadratic growth is you have an intercept, right, a beta 0, a starting point, and then you have a slope function that applies to the square of time. So at time 1, for example, your growth is just whatever this growth parameter is. But at time 2, it's actually 2 squared, so it's actually 4 times what this growth parameter is. At time 3, it's actually 3 squared, so it's 9 times. So as you can see, it's getting exponentially faster, right? In this case, something is changing exponentially faster. You see this kind of a pattern, by the way, quadratic growth. You don't see it as much in the social sciences because we rarely observe things that change that fast. Exponential growth, or quadratic growth, I should say, exponential growth could be any kind of, raised to the second power, third, fourth, just at an exponent. But very few things in social science change that fast. So if you think about beliefs or attitudes, right, we rarely see that kind of like exponential shift. It's usually more of a gradual change over time. But that's very good, especially in the hard sciences, for example, where you have things like noble gas laws and other sorts of physical principles that are pretty fixed in terms of their relationships. You do see quadratic change much more often. And then we have like these kind of hybrid growth patterns, which are much more common in the social sciences. So these are the ones we typically end up seeing. So there's what I call higher order growth 1, and that is a linear plus a square or quadratic term. And the functional form there is you have an intercept, you have some impact of time, which is beta 1, and then you have some impact of time squared, and this should actually be B2, not B1. This should be B2. So you actually have, what happens is over time, this starts to flatten out a little bit. So this is a really fast start, and then the curve starts to flatten out and become more linear over time. This is a very common trend that you see in the social sciences. This is one we test a lot. And then there's an even more complex form of this, which is linear and square and cubic. So cubic, of course, is the cube of time. And here it sort of starts out aggressively and kind of narrows down and then takes off again. And so this should be beta 1, beta 2, beta 3 instead of beta 1. So beta 1 times time plus beta 2 times time squared plus beta 1 times time cubed. So as you can see, what we're doing is we're adding some of these higher order time components to hopefully sort of better describe the pattern of change that we see in our data. And we have the ability to do this really easily in MLM, which is quite nice. Okay, so let's talk about this in terms of the notation. So this was the notation that we learned last week for a growth model. So we have T's and I's in this model. So we have person I, who is at level 2, and time T, which is at level 1. So we have observations or times that are nested within individuals. And so the level 1 equation is actually at the observation level. So these are observations that are nested, in this case, within students. And those coefficients at the bottom level are pi's. So before it was betas, and then it was gammas. So here we have pi's. And so everything basically moves up a level. This is stuff that we talked about last week. So everything that was 2 weeks ago. The pi's are our level 1 slopes, and the betas are our level 2 slopes. And so basically what this means is, a score for a given student I at time t is a function of some starting point, which is pi 0I, plus some growth parameter times time. So in this case, this would be a linear growth model. So for each increment of time, we're seeing change according to this pattern. And then, of course, we have a random effect at level 1 to explain variability at the observation level. And then at level 2, we have a person-specific random term for the intercept and a person-specific random variability for the slope, which is, so each student essentially can have their own intercept and their own slope. So that is the standard sort of approach for a growth model. So if we wanted to do a quadratic growth model, which is one that we talked about a little bit, really all that changes here in this whole model, instead of time, we just account for time squared. Everything else is pretty much the same. So now we have a starting point. So a score for student I at time t is a function of a starting point, which is here, pi 0I, plus some growth parameter times the square of time. So again, that squaring effect, as you go to higher levels of time, you're essentially assuming a very aggressive slope, kind of a curving slope in change over time. You can also do a combination of the two, which is really what we're going to test today, and that is a linear plus a quadratic growth. So in order to do that, we have a term for time plus a term here for time squared. So we actually put both of those in the model together, and we can actually put a third term in for time cubed if we wanted to do that as well. So that's how that works in terms of the statistical notation. All of these changes in the higher order growth model generally are happening at level 1, at the observation level. Level 2 stays basically the same, although we have some additional predictors down here if we add additional predictors, but otherwise it stays basically the same. Okay, so I do want to point out I have some examples here which I'll be walking through on the video, but if you don't want to watch the whole video down the road, and you're like, oh, I forget how to interpret everything, I have annotated output here in Stata. So this is a model predicting math achievement with a linear component, that's year 0, a squared or quadratic component, that's year squared, and then a cubic component, which is year cubed. So those are all down here. And then I have a random slope, in this case just for year 0, although you could add some of those other components as well. So I have that in Stata, and I also have an equivalent setup going in R. Now R people, you will learn when you get to the video, womp womp, in order to fit, oh no, actually you can fit this one in LME4. It's the later example you can't. So yes, you can do this in LME4, the same package we've been using before. You can fit these higher order growth parameters as well. Okay, so note of caution before I go. If you really want to show evidence of nonlinear growth, you actually need a ton of data. And most of the time, you don't have enough waves of data to confirm that it's actually real. So I have sort of a rule, which I've borrowed from other folks. If you only have 3 time points, so if you've only observed people at 3 time points, I would only test linear growth, because it's really hard to show anything other than linear growth with 3 time points. If you have more than that, if you have, say, 4 to 6 or more, you can absolutely and should absolutely try nonlinear growth, and that's perfectly fine. But with only a few time points, you can make anything look nonlinear. And so this is an example. I love this. If you're a podcast person, I highly recommend a podcast called Quantitude. It's like attitude, but with quant. It's hosted by Greg Hancock and Patrick Curran, who are 2 just awesome methodologists, and just really kind of funny kind of hosts as well. And so they often post funny things on Twitter. So here's a funny post. So they said, we picked 2 time points, and then we fit an exponential growth function to the number of Quantitude listeners with only 2 time points. The model predicts that by next Tuesday, Quantitude will have been heard by everyone on the planet, plus or minus. So even if a bit premature, thank you, people of Earth. So just an example, with only a few time points, you really are limited in what you can do. They also make some very funny memes, which are kind of funny on Twitter. So here's some breaking news, some advances in data science. A baby lemur has been trained to actually run factor analysis using SPSS. Just a nice little dig there at SPSS. We love SPSS, but I just like that. I thought that was kind of funny. So anyway, that is part 1. So nonlinear, adding nonlinear terms to your data. Part 2, we'll talk about what are called heterogeneous variance models. We'll get into that a little bit as well, but that is it for part 1, and we will take it from there. Thanks.